Today is direct proof and counterexample 4, divisibility. When you were first introduced to the concept of division in elementary school, you were probably taught that 12 divided by 3 is 4, because if you separate 12 objects into groups of 3, you get 4 groups, nothing left over. It also taught that this is saying 12 is evenly divisible by 3, or 3 divides 12 evenly. The notion of divisibility is the concept of one of the most beautiful subjects in advanced mathematics. I don't know if I'd call it beautiful, but whatever. Number theory, the study of properties of integers. Definition. If n and d are integers, then n is divisible by d if and only if n equals d times some integer and d does not equal to 0. You can also say n is a multiple of d, d is a factor of n, d is a divisor of n, or d divides n. The notation is d type n is read d divides n. Symbolically, if n and d are integers, d divides n if and only if there exists an integer, say k, such that n equals d k and d does not equal 0. This notation reads d does not divide n, the pipe with the slash through it. Okay. All these questions here. 21 divisible by 3? Yeah. 5 divides 40? Yeah. 7 divisible divides 42? Yeah. Is 32 a multiple of negative 16? Yeah. Yeah. 16 times negative 16 times negative 2. They're both integers. Yeah. It's not just positive integers. Oh, okay. Yeah. 32 is a multiple of negative 16. 6 is a factor of 54. Yeah. 7 a factor of negative 7. Yeah. Negative 1 is the, because 7 times negative 1 is negative 7. So, yes to all of the above. So, if k is any non-zero integer, does k divide 0? Yes, because 0 equals k times 0. 0 is an integer. Two useful properties of divisibility are: 1, if positive integers divides a second positive integer, then the first is less than or equal to the second. And 2, that the only divisors of 1 are 1 and negative 1. So it gives you 2 theorems to use in proofs. You should probably write these theorems down for later use in the homework and quiz and tests. If a and b are integers, is 3a plus 3b divisible by 3? Yeah, because you can factor out the 3, and then a plus b is an integer because the sum of integers is an integer, and you can have the 3 as a multiple of an integer. If k and m are integers, is 10km divisible by 5? Yeah, because 10 is divisible by 5. And you would leave you with 2km, which is an integer, if k and m are integers, because of multiplication of integers are integers. Yeah, the associative law of algebra gives you 5 times 2km, and 2km is an integer because it is product of 3 integers. When the definition of divides is rewritten formally using the existential quantifier, the result is D divides N if and only if there exists an integer k such that N equals dk and D does not equal 0. Since the negation of an existential statement is universal, it follows that D does not divide N if and only if for all integers k, N does not equal dk or D equals 0. In other words, the quotient N over D is not an integer. Does 4 divide 15? No, because it's not, the quotient is not an integer. 3.75. An alternate way to define a prime number is to say that an integer n greater than 1 is prime if and only if its only positive integer divisors are 1 and itself. So now proving properties of divisibility. Prove that for all integers a, b, and c, if a divides b and b divides c, then a divides c. Well, it's already written formally, so you can immediately pick out a starting point or the first sentence of the proof and the conclusion that must be shown. Starting point. So suppose a, b, and c are particular but arbitrarily chosen integers such that a divides b and b divides c. Show that a divides c. Or in other words, c equals a times some integer. So since a divides b, b equals ar for some integer r. Since b divides c, c equals b times s for some integer s. Now, this equation expresses c in terms of b and the equation b in terms of a. Thus, you can substitute this equation for the b in the second equation. So you're left with c equals a r s. By the associative law of multiplication, that can be written as c equals a times the quantity rs. Now, it only remains to be certain to verify that something that r and s is an integer. But of course, because it's a product of 2 integers, it is an integer. So the theorem of transitivity of divisibility is for all integers a, b, and c, if a divides b and b divides c, then a divides c. Divisibility by a prime, any integer n greater than 1 is divisible by a prime number. Counterexamples and divisibility. Is the following statement true or false for all integers a and b if a divides B and B divides A, then A equals B. Is that true? Can you find a counterexample to indicate that it wouldn't be true? Yeah, so it doesn't fit. So, well, the statement is false. Following discussion describes a mental process that may take just a few seconds. It is helpful to be able to use it consciously, however, to solve more difficult problems. Start off with what you, as if you were trying to prove it. So, suppose A and B are integers such that A divides B and B divides A. Must it follow that A equals B, or could it happen that A and B are not equal for some A and B? Focus on the supposition. What does it mean? It means that B equals HA and A equals KB. All right. Some integer A, or some integer times A equals B, and some integer times B equals A for some integers H and K. So this implies that B equals HA, which is HKB, which equals HK times B. B can't be 0. So 1 equals HK. Divide both sides by B. So H and K are divisors of 1. By theorem 4.4.2, the only divisors of 1 and 1 are 1 and negative 1. Thus, A and K are either both 1 or both negative 1. If H and K equal 1, then B does equal A. But if H and K equal negative 1, then B equals negative A, and so A does not equal B. That's the counterexample. Here is a formal answer. Proposed divisibility property. For all integers A and B, if A divides B and B divides A, then A equals B. Counterexample. Let A equal 2 and B equal negative 2. Then negative 2 times negative 1, or equals negative 1 times 2, and 2 equals negative 1 times negative 2. So A and B are not equal because 2 does not equal negative 2. Therefore, the statement is false. Unique factorization of integers theorem. The most comprehensive statement about divisibility of integers is contained in the unique factorization of integers theorem. This theorem is also called the fundamental theorem of arithmetic. The unique factorization of integers theorem says that any integer greater than 1 is either prime or can be written as a product of prime numbers in a way that is unique, except for perhaps the order in which the primes are written. So 72 equals 2 times 2 times 2 times 3 times 3. Or change up the order. The 3 2's and the 2 3's may be written in any order, but any factorization of 72 as a product of primes must contain exactly 3 2's and 2 3's. No other collection of prime numbers besides that multiplies out to 72. Given any integer n greater than 1, there exists a positive integer k. Distinct prime numbers p1, p2, yada 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 to pk, and positive integers e1, e2 to ek, such that n equals p1 to the e1 power times p2 to the e2 power times p3 to the e3 power, yada 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 to pk to the ek power. Any other expression for n as a product of prime numbers is identical to this, except for perhaps the order in which the factors are written. The standard factored form is the p1, p2 to the e1, p2 to the e2, so forth to pk to the ek, where k is a positive integer. P1, P2, and up to pk are prime numbers, and the E1, E2, E to the ek are positive integers, and P1 is less than P2, which is less than P3, which is less than P4, yada yada to pk. So the standard factored form would start with the smallest prime first, raised to whatever power it needs to be raised to, followed by the next lowest prime, raised to its power, so on and so forth. Write 3,300 in standard factored form. That would be 33 times 100, or 3 times 11. Let's see if the board will cooperate with me today. So it would be 100 times 33, and then 10, 10, 3, 11. So 2, 5, 2, 5, 3, 11. 2 squared times 3 times 5 squared times 11. See, the primes are done in order of from lowest to highest, and rather than duplicating prime factors, you raise them to the appropriate power. So you get 2 squared plus 3 times 3 times 5 squared times 11. Suppose m is an integer such that 8 times 7 times 6 times 5 times 4 times 3 times 2 times m equals 17 times 16 times 15 times 14, 13, 12, 11, 10. Does 17 divide m? Well, 17 is a factor in this side because the is a prime, and it is a factor on this side. But since all of these numbers here are lower than 17, it doesn't divide those, so it must divide m. There's also a prime factor of the left-hand side. But 17 does not equal any prime factor of those other factors because it is too large. So 17 must occur as one of the prime factors of m. So 17 divides m. And that is divisibility. They use the word beautiful to describe this. I don't know if I would agree with that, but it's interesting. And we can move on to 5, the section 5. Elementary number theory continues with direct proof and counterexample 5, division into cases, and the quotient remainder theorem. Now, it's going to start with the the quotient remainder theorem. Given any integer n and positive integer d, there exist unique integers q and r such that n equals dq plus r, and r is greater than or equal to 0 but less than d. So if n is positive, the quotient remainder theorem can be illustrated on this number line. Some quantity times d plus r equals n. Division into cases. If n is negative, the picture changes. Since n equals dq plus r, where r is non-negative, d must be multiplied to a negative integer q to bring dq either exactly to n, in which case r is equal to 0, or a point below n on the number line, in which case the positive integer r is added to bring dq plus r back up to n. So some quantity times d, some negative integer times d, is less than n, plus r brings it back to n. So the quotient is not the same as if n is positive. For each of the following values of n and d, find if integers q and r such that n equals dq plus r. Okay, so n equals 54, d equals 4. Let's try my luck at this again. So 54 equals 4q plus r. All right. So you would how would you solve that? What's the next step? You can take q to be what 13. Equals 54 equals 52 plus r, and then r equals 2. Did I do my math right? Does that look right? Four times 13 is 52, right? Okay. So yeah, find the it's basically like long division that you learned in 4th or 5th grade or whatever it was. Or do they still teach that now? Long division? Yeah. Okay. The Common Core stuff is they screwed up math education, in my opinion, with that. So I don't know what they're teaching nowadays. But oh, come on. Oh, yeah. So Q is 13 and R is 2. With a negative 54, you need your Q to be negative 14, so the 2 will bring it back up to 54. And N is 54, D is 70. So it's Q is 0 and R is 54. So div and mod. Given an integer n and a positive integer d, n div d means the integer quotient obtained when n is divided by d. And n mod d equals the non-negative integer remainder obtained when n is divided by d. Symbolically, n and d's, and if n and d are integers and d is greater than 0, then n div d equals q, n mod d equals r, such that n equals dq plus r, where q and r are integers and r is between d and 0. Compute 32 div 9 and 32 mod 9 by hand or with a four function calculator. Well, this harkens back to fifth grade math, where you do division and come up with a remainder instead of a decimal. So long division yields a 3 with a remainder of 5. On a four-function calculator, compute n div d for non-negative integer n and a positive integer d. Just divide n by d and ignore the part of the answer to the right of the decimal point. Compute the mod. Substitute n div d in place of q and n, in place of q, and n mod d in place of r in the equation. dq plus r equals n. The result is d times n div d plus n mod d. Solving for n mod d gives n minus d times n div d. So gives you 27 for 32 div 9 and 5 for 32 mod 9. Prove that if n is a positive integer, then n mod 10 is the digit in the ones place in the decimal representation of n. All right, so suppose n is any positive integer. The decimal representation for n is dk dk minus 1, dk yada 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 to d2, d1, d0, where the d's are integers from 0 to 9 inclusive, and dk does not equal to 0 unless n equals 0 and k equals 0. All right, so n equals dk times 10 to the k plus d sub k minus 1 times 10 to the k minus 1 plus however many digits, plus d2 times 10 squared plus d1 times 10 plus d0. d0 is in the digits, is the digit in the ones place. Factoring out the 10 from all but the final term gives this. Thus, n equals 10 times some integer, because all those are integers, plus d0, so n mod 10 equals d0, which is the digit in the ones place in the decimal representation for n. We didn't really look at that one. Representations of integers. We defined an even integer to have the form twice sum of some other integer. At some point in time, we could have defined an odd integer to be one that was not even. The fact that any integer is either even or odd is called the parity property. Prove that given any two consecutive integers, one is even and the other is odd. Two integers are called consecutive if and only if one is one more than the other. So if integer m, one integer is m, the next consecutive integer is m plus 1. So to prove the given statement, you divide the analysis into two cases, where the smaller of the two integers is even, and where the smaller of the two integers is odd. So in this case, m equals 2k for some integer, so m plus 1 equals 2k plus 1, which is odd by definition of odd. Hence, case 1 is the statement is true, because one of m and m plus 1 is even and the other is odd. Case 2, if m is odd, m equals 2k plus 1 for some integer k, so that m plus 1 equals 2k plus 1 plus 1, which equals 2k plus 2, which equals 2 quantity k plus 1. But k plus 1 is an integer because it is the sum of two integers. Therefore, m plus 1 equals twice some integer, and thus m plus 1 is even. So the other case is shown to be true, that one of m and n plus 1 is even and the other is odd. It follows that regardless of which case actually occurs for the particular m and n plus 1 that are chosen, one of m and n plus 1 is even and the other is odd, which is what it was to be shown. So the parity property is any two consecutive integers have opposite parity. Prove a statement of the form, if A1 or A2 or AN, then C, prove all of the following. If A, then C, if A2, then C, and so forth to AN, then C. This process shows that C is true regardless of which of the A's happens to be the case. That's by proof by division into cases. Finally, well, not finally, but next we show that any integer can be written in one of the four forms. N equals 4q, n equals 4q plus 1, n equals 4q plus 2, or n equals 4q plus 3 for some integer q. Okay? So the solution. Given any integer n, apply the quotient remainder theorem to n with the divisor equal to 0. To 4. This implies there exists an integer quotient q and a remainder r such that n equals 4q plus r, and r is less than 4 but greater than or equal to 0. The only numbers that satisfy that are 0, 1, 2, and 3. Hence, n is equal to 4q plus 1 or plus 2 or plus 3 or plus 0. In other words, n mod 4 equals 0, 1, 2, 3, 0, 1, 2, or 3. Now the square of an odd integer. The square of any odd integer has the form 8m plus 1 for some integer m. Well, let's see here. Develop the proof by asking where am I starting from? What do I need to show? Rewrite the statement more formally. For all odd integer n, there exists an integer m such that n squared equals 8m plus 2 or plus 1. From this, you can immediately identify the starting point and what is to be shown. Suppose n is a starting point. Suppose n is a particular but arbitrarily chosen odd number. And show that there exists an integer m such that n squared equals 8m plus 1. That would say that n squared minus 1 divided by 8 is an integer. Or that 8 divides n squared minus 1. Perhaps you could use the fact that n squared minus 1 equals n minus 1 times n plus 1. Does 8 divide n plus 1 times n plus? No, it's supposed to be minus 1. The n minus 1 times n plus 1. Since n is odd, both n minus 1 and n plus 1 are even. That means our product is divisible by 4. Need to show that the product is divisible by 8. Any ideas on how that might be done? They don't say in the slides. But you could try another approach by arguing since n is odd, you can represent it as 2q plus 1 for some integer q. Then two q plus 1 squared equals n squared, which equals 4q squared plus 4q plus 1, which is equal to 4 times the quantity q squared plus q plus 1. It is clear from this analysis that n squared could be written as a form of 4m plus 1, but it may not be clear that it can be written as 8m plus 1. All right. Yet another possibility is to use the result of 4.5.6. That example showed that any integer can be written in one of the 4 forms: 4q, or 4q plus 1, 4q plus 2, or 4q plus 3. Two of these are odd, 4q plus 1 and 4q plus 3. Thus, an odd integer can be written in the form of 4q plus 1 or 4q plus 3 for some integer q. You could try breaking it into classes based on these two different forms. And I'll leave it to you to solve that, do that proof. Maybe it'll come up on the test. But it is true that the square of any odd integer has the form of 8m plus 1 for some integer m. But absolute value and the triangle inequality. The triangle inequality is one of the most important results involving absolute value. It has applications in many areas of mathematics. For any real number x, the absolute value of x, denoted by pipe x pipe, is defined as follows. Absolute value of x equals x if x is greater than or equal to 0, and it is equal to minus x if x is less than 0. For every real number r, negative absolute value of x is less than or equal to r. The negative absolute value of r is less than or equal to r, which is less than or equal to the absolute value of r. For every real number, the absolute value of negative r is equal to the absolute value of r. And for all real numbers, x and y, the absolute value of x plus y equals the absolute value of x plus the absolute value of y. Or, I'm sorry, is less than or equal to the absolute value of x plus the absolute value of y. And I believe that's it for that. They don't get into that many proofs. I'm thinking this example will be a homework assignment. Finish the proof. It started it in the subsequent slides. Gave you some ideas of which way to approach it, but can you prove it? Finish the proof. So I'm going to post this on Canvas this afternoon. I'll have it due next Tuesday on paper, paper submission, and because doing symbols and stuff like that might be challenging. Well, you could. I'll do paper submission or a Canvas submission, but I'll have it due for next Tuesday before class. Okay. All right. That should about wrap it up for today. Have a good day. We'll see you back on Thursday.